Question 5a. Nitroxyl chloride can be formed by this nitrogen monoxide and the chlorine. The initial rate of this reaction is investigated, and table 5.1 there are 3 experiments there. We need to use these experiment results to deduce the orders of the NO and the chlorine. So let's start with the easy one, the orders for the nitrogen monoxide. So we use the experiment 1 and 2. So we compare these two. When the concentration of the NO times 3, the rate times 9, and the concentration of the chlorine is the same. So means the initial rate here is only affected by the change in the concentration of the NO. So it's very clear that the orders for this NO is second orders, because when concentration times 3, the rate times 9 is 3 squared, right? So it's actually second order, right, for this NO. And after that, we can compare the experiment 1 and the experiment 3. So this one and this one. So when we compare these two experiments, the concentration of the NO and the chlorine, they are different. But it's okay because we already know the orders for the NO. So let's look at the green color one, this one. In this experiment 1 and 3, so we know that from this experiment 1 to 3, the concentration of the NO is times 2, and the concentration of the chlorine times 4, and the rate is times 16. And we already know that the orders for this NO is second order, means when this concentration double, the rate will be times 4. So means the rate will be 2 squared times 4. And because now it's 16 times, we can do a simple calculation first. So 16 over 4. 16 over 4. So we will get, of course, 4 times. Right? And this 4 times is now from the increase in the concentration of the chlorine. So now the concentration of chlorine, the concentration is increased 4 times, times 4, and the rate also times 4, because we already eliminate the contribution from this NO. So means when concentration times 4, rate also times 4, we know that the chlorine is a first order. So that's why we have this answer, right? Okay. So compare 1 and 3. When concentration of the NO double and the chlorine times 4, the initial rate is times 16. So we know that the chlorine is the first order, because we already get the orders for of the NO just now. Part 2. Use rate equations from the A part 1, which is this one, the rate equation. Rate equal to the K constant times the concentration of NO square times the concentration of the chlorine. Okay, so and is asked to use the result, the data from experiment 1. You just need to substitute the initial rate in the experiment 1 and both concentration. So you should get 3925.3. And it's asked the units also. So the rate, you need to know the rate is mole per dm cube per minute. So use this one together with the 2 concentration, means this one. Therefore it's a mole per dm cube per minute over mole per dm cube cube. So eventually you get dm6 mole negative 2 per minute. Right. So this is a unit. Okay, so part B. NO2Cl is another compound containing nitrogen, oxygen, and chlorine. In sunlight, NO2Cl can undergo homolytic fission, means the covalent bond break and the electrons in the covalent bond will go to different atoms. So this we call homolytic fission, means the electrons it will equally share, or it will go to two different atoms, right, like this one, and release chlorine radicals, which can catalyze the conversion of ozone into oxygen. Complete the mechanism for this process. So we have the initiation, propagation two steps. Okay, so initiation already told you is a homolytic fission. So means the NO2Cl now need to undergo homolytic fission. It's telling you chlorine radicals will form. So this is the NO2Cl. So the NCl bond will break homolytically. The electrons here in the covalent bond, one electrons will move to the nitrogen, another electrons will move to chlorine, and will form these chlorine radicals and these NO2 radicals. Because it say that the chlorine radicals will help, or will cause the ozone turns to oxygen. So for the propagation, we just need to use the chlorine radical. So the chlorine radical will react with the this ozone, something like this. This is actually extra. If you not really understand, it's okay. So this is the ozone molecule. First, these chlorine radicals will form a bonding with one of the oxygens here. So it's something like this. So this unpaired electron, or these electrons will combine with another electrons from this the oxygen, right, to form the radical. And of course, at the same time, this pair of electrons will move to these oxygens to form this pair of electrons will move to these oxygens with charge positive to form the oxygen. And because one electrons use up to form this bonding, so the oxygens now it has one unpaired electron. So this is the CLO radicals that produce. That's why it forms this CLO radical with oxygen. And this CLO radical will further react with the ozone and reform the chlorine radical. So it's something like this. So when these CLO radicals approach another ozone, so these CLO will undergo the homolytic fissions, and one electrons will move to chlorine to form back the chlorine radical, and one electrons will move to this oxygen to form oxygen's atom, and this OO bond break, so this electron move to these oxygens with charge positive to form the O2 right here, and these two oxygens will form another oxygen's molecule. So that's why it will form two O2 here. Okay, so this is the complete mechanism. So the initiation, propagation, and this the first step and second step. Okay, so it will form at the end it will just form the oxygens from ozone to the oxygen. Part C, ozone reacts with nitrogen dioxide as shown. So this one is you need to propose the two-step mechanism. The rates of the reaction is the first order with respect to the ozone, and the first order with respect to the NO2. So let's make the step 1 as a rate determining step. So because it's already mentioned, NO2 is a first order and the ozone is first order. Okay, in this rate determining step, the first step, so we put the ozone and NO2 each 1 mole on the left hand side. So this one is to tell or to indicate the the orders of these reactant. So because when we put the numbers of mole, certain numbers of mole of reactants on the left hand side of the rate determining step, the numbers of mole is represent the order. So because it's 1 mole each, so they are first order. Okay, so this is the first step that you need to do. You put the ozone and the NO2 each 1 mole on left hand side. After that, you need to do the second step. You put this one first. You put the N2O5 plus O2 in this step 2 product side. Then you continue with this part and this part. Okay, O3 with NO2, you just combine them, it will form NO5. NO5 is an intermediate. You bring it to the second step, the reactant side, and this one will react with the NO2. Why? Because in this overall equation, there are 2 moles of NO2. So in order to balance the equation, so the step 2 left hand side, you must put 1 mole of NO2. Therefore, at the end, you'll get 2 NO2. Right? So the NO5 now eliminate. You sum up left to left, right to right, you get back the equation. So this is a complete 2 steps mechanism for the reaction above. Okay, that's all. Thank you.